So this week we'll be talking a bit about atmospheric stability, and I figured it'd be nice to go through a couple of the slides to really talk about some of the key points of the atmosphere and atmospheric stability. So one of the key, just absolute things to keep in mind when we're talking about the atmosphere is warm air rises and rising air cools. And there's a video that you can see right here, if you choose to go to it, that might help with a little bit of that understanding. But this, if you keep this in mind, it will help a great deal with the entirety of this lesson. Another thing to keep in mind is the atmosphere always wants to be in equilibrium. And there are two types of equilibrium that we're going to talk about. Stable equilibrium, and you can think of that as a rock at the bottom of a hill. If you spend a lot of effort pushing the rock up the hill and then stop, the rock will want to roll down. It's stable. The rock always wants to go back to its starting position at the bottom of the hill. Now, if you start with a rock at the top of the hill, it would be an unstable equilibrium, because if you put any work in and push the rock out of that position, it'll start to roll downhill. It will speed away from or go away from its starting position. So the way to think about this is a stable equilibrium, the atmosphere wants to go back to its original state. An unstable equilibrium, the atmosphere wants to move away from its original state. So in doing the reading, you'll talk a little bit about parcels of air. And we won't go over this too much, but basically it's a volume of air that has a set amount of material in it. So it's just a balloon. Think of it as a balloon of air. You're not allowing things to pass in and out of it. Does not break apart either. And it cannot mix heat with the air between external air and internal air. So it's basically a separate pile of air. And again, just to keep in mind, the average speed of molecules is directly related to air temperature. That will help understand that. So if you think about it, warm air rises. So you have a parcel of air right here, a certain amount of molecules in it. It's warmer than its surroundings. It will try to rise. And as it rises, it can take up more space. There's less pressure, less dense air around it. So it will start to be bigger. And in doing so, the molecules will not be bumping into each other as much. They will move more slowly, and it will cool down. But if it's still warmer than its surroundings, it will continue to rise. And again, it will take up more space. The molecules won't move as quickly, and it will be cooler yet. That's the process of warm air rising, rising air cooling. And you can think of this happening in the opposite direction too. So a rising parcel of air expands and cools. A sinking parcel of air, so if you take a parcel of air up in the atmosphere and bring it down, it will compress and warm. So how much does it warm or cool depending on which direction you're going? And it depends if it's dry or saturated. So in the dry case, you have through a variety of equations, a set amount. For every kilometer or 1,000 meters you go up in the atmosphere, a parcel will cool by 10 degrees Celsius. For every kilometer you go down, it will warm by 10. If you have a saturated parcel, you will have a moist adiabatic lapse rate. And the equations are a little complex. You will never have to look at those in this class. It's just a good thing to remember that it will end up being approximately 6. So 6 degrees cooler as you go up in the atmosphere, or 6 degrees warmer as you go down in the atmosphere. And the difference is because of latent heat. So as you're moving up in the atmosphere, the parcel will cool. If it reaches saturation, it's going to start condensing water out into water droplets. That condensation releases latent heat, counteracting some of that cooling, and bringing it from the 10 of dry to the approximately 6 of the moist adiabatic lapse rate.